All right, so today we're going to be going over the chain rule. We're going to look at this standard of our calculus standards 5.0. Students know the chain rule and its proof and applications to the calculation of derivative of a variety of composite functions. Okay, so kind of straightforward. We're just going through the chain. Today's content objective is students will be able to solve simple chain rule applications. Our language objective. Students will differentiate simple composite functions using the chain rule in worksheet exercises and in pairs. And a lot of that's not for today. We're going to see that tomorrow when you guys come back into class. One thing that we're going to have to look at, though, is something that we probably haven't looked at in quite some time, our composite functions, okay? So take a quick minute. I want you to go onto YouTube and I want you to follow this link. You can either type it in, or I have hopefully posted the YouTube link below on the description. So go ahead and watch that full video. You can pause this and then come back to it whenever you're done. Okay, so now on to the chain rule. So the chain rule is one of the rules we need to use in order to calculate certain derivatives, especially when we're looking at composite functions. This is going to be used similar to the things like the product rule and the quotient rule that we've learned before. So here's the formal definition of the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function capital F equals f composed of g defined by capital F of x equals the composite function of f of g of x is differentiable at x, and f prime, or the derivative of f, is given by the product. So what we really need is this right here. This is going to be our main equation for solving derivatives for chain rule functions. So we have that the derivative of capital F of x is going to be the derivative of f with g of x composed inside multiplied by the derivative of g of x. Okay, so we're going to be able to find the derivative of f and the derivative of g. Okay, and we're going to go through a couple examples just so that we're comfortable using this equation. Okay, so the steps to solving the chain rule are going to be as follows. First, you're going to have to be able to identify f of x and g of x, okay, because we're going to be given the composite function. We're not necessarily going to be given the composite parts. And then we're just going to check to make sure that we found f of x and g of x correctly. So in order to do that, we're actually going to evaluate f of g of x. Then we're going to apply the chain rule, and that's going to be as follows. First, we're going to evaluate the derivative of f with g inside. We're not necessarily going to touch g yet. We're going to run into that in just a second. And then we're going to evaluate the derivative of just g. We're not doing anything with f of x, okay? And lastly, we're just going to take those two parts and we're going to multiply them together to find the product of the derivative of f given g of x and the derivative of g of x. Okay, so let's see how that works in this example here. So example 1, we're going to find the derivative of big f of x if big f of x equals 2x plus 4 all squared, okay? So first thing that we're going to do is we're going to identify f of x and g of x. So the easiest way to do this is to establish what is your inner function and what is your outer function. If we look at this equation here, we see an inner function. Our inner function should be 2x plus 4. And our outer function is what we're doing to our inner function. Well, it looks like we're squaring our inner function. So we have two functions. We have 2x plus 4, and we're squaring something. That means that our outer function, or f of x, is going to be x squared. Okay? And I'm getting x squared because whenever we plug this 2x plus 4 into x, it should look like that. So we're kind of replacing 2x plus 4 with x because 2x plus 4 is our g of x. So if we were to plug in 2x plus 4 into 2x squared, we should get our function there, 2x plus 4 squared. So let's take a look. Let's make sure that we're right with our two functions. So we're just going to evaluate this by plugging them in. So first, you're going to take f of g of x. And remember, when we work with composite functions, we work from the inside out. So we're going to plug in 2x plus 4 where g of x goes, right? And then we're going to evaluate f of x for 2x plus 4. So we plug 2x plus 4 into x squared, and we should get 2x plus 4 squared, which matches our original equation. So f of x and g of x work. Now we're just going to apply the chain rule. So first step, remember, is we're going to evaluate f prime of g of x. Now this might seem a little bit weird with the notation, but it's pretty straightforward, nothing crazy. We'll get used to it as we go through our examples, okay? So we're just looking at this part. If we have 2x plus 4, sorry that it's kind of sloppy, it's a little weird to write on with a mouse. Okay, so this is what we're taking the derivative of. But if you just think about the f of x part, remember that f of x was just x squared. So normally, the derivative of x squared would just be 2x, because we bring the exponent down in front. Remember your power rule, and you subtract the exponent by 1. So we kind of apply the similar aspect to our derivative here, where we took the 2, brought it up in front, and we subtracted the exponent by 1, leaving g of x the same. We didn't change that at all. And then I just simplified, you can distribute that 2, so that we get 4x plus 8. Now that we have that, we're going to have to evaluate g prime of x. Now this might be pretty simple, just because we're only looking at one function. So if we take the derivative of g of x, the derivative of 2x plus 4 is just 2. Okay? And now the last step is we need to find the product of those two derivatives that we found. So we need to take f prime of g of x and multiply that by 2. And when we do that, we get 4x plus 8 times 2, and we get 8x plus 16. Therefore, we should get that the derivative of big F of x is just 8x plus 16. Now, you might ask, why don't we just FOIL this out? Why don't we just take 2x plus 4 squared and multiply it by itself twice? Because if we did that, we wouldn't necessarily need the chain rule, which is true. You could multiply it out and solve for the derivative the standard way that we have been doing, but that's not always going to be the easiest way to do it. So if we look at our next example, example 2, we're going to find f prime of x, big F prime of x, if big F of x equals x cubed plus 1 to the 100th power. Now, I wouldn't suggest multiplying x cubed plus 1 by itself 100 times, because that would take a long time, and it's a little bit unnecessary. That's why we like the chain rule, because it's a lot quicker and more efficient way to solve for the derivative. So step 1, identify f of x and g of x. So our outer function here, well, let's look at our inner function. Usually that's a little bit easier to identify. Inside we have x cubed plus 1. And so our outer function, what we're doing to that function is we're taking it to the 100th power. So our outer function should just be x to the 100. We're taking a function to the 100th power. Our inner function should just be x cubed plus 1. Okay? So now let's check that. Let's evaluate f of g of x to make sure that we got the correct f of x and g of x functions. So we plug that in, plug in x cubed plus 1 for g of x, plug x cubed plus 1 into f of x, and we should get x cubed plus 1 to the 100th power. That matches our original function, so we're doing it right so far. So we're going to apply the chain rule. So first, evaluate f prime of g of x. So we take the derivative of just the f part. Oops, looks like there's a little error there. We should bring the exponent out in front, so we have 100 as our coefficient, leaving g of x the same, and then we subtract our exponent by 1, so it should be to the 99th power. Okay? sorry about that. And then we're going to take the derivative of just g of x. Okay, so if we take the derivative of x cubed plus 1, we should just get 3x squared. All right, and then the last step, we're going to multiply our two derivatives together. 100x cubed plus 1 to the 99th power times 3x squared. So if we multiply those together, and again, sorry about that, the exponent should be 99. So if we multiply them together, 100 times 3x squared, we're going to combine those because we can multiply those together. They're not bound by an exponent. We get 300x squared by multiplying these two together. And then we're just going to leave this x cubed plus 1 to the 99th power. We don't necessarily need to multiply that out. This would be considered its simplified form. Therefore, we get that the derivative of big F of x is 300x squared times the quantity x cubed plus 1 to the 99th power. Okay? So let's go to example number 3. This time we're going to differentiate y equals the square root of x squared plus 3x minus 5. First, we're going to have to identify f of x and g of x. So let's look for the inner function. And it looks like we have an inner function x squared plus 3x minus 5. Square roots tend to be a little bit easier because you can actually see that it is inside the square root, where the outer function is just our square root. So we would say that f of x is the square root of x. And for derivative purposes, we can write that as x to the 1/2 power. And then g of x is just the inner function, x squared plus 3x minus 5. So we're going to evaluate f of g of x to make sure that f of x and g of x are correct. So you plug in g of x squared plus 3x minus 5. Plug that into f of x, which is our square root of x. So we get the square root of x squared plus 3x minus 5. And those look like they match. So we're going to move forward. Then we're going to apply the chain rule. So let's evaluate the derivative of f in terms of g of x. So we take our exponent, we brought it out in front, our 1/2 exponent, left g of x on the inside, didn't change that, and then we subtracted our exponent by 1, which should give us negative 1/2. So that would just be the derivative of f in terms of g of x. And then we're going to evaluate the derivative of just g of x. So if we take the derivative of x squared plus 3x minus 5, use your power rule, you can end up with 2x plus 3. Pretty straightforward. And then the last step is we're going to take the product of those two derivatives. 1/2 times the quantity x squared plus 3x minus 5 to the negative 1/2 power times 2x plus 3. So we multiply those two products together, and we should end up with 2x plus 3 is going to stay here in the numerator. This 1/2, the 2 stays in our denominator. And right here, we're going to send this down to the denominator because of our negative 1/2 power. The negative tells us send it to the denominator. The 1/2 tells us take the square root. So we should end up with the derivative of y as 2x plus 3 over 2 times square root of x squared plus 3x minus 5. So that's where chain rule also comes in handy, is when you're taking the square root or cube root or any other kind of root of a function. All right. So I believe this is our last example. We're going to differentiate y equals the quantity 4x plus x to the negative 5th all to the 1/3 power. Now you could rewrite that as the cube root of all that, but it's not necessary. So we're going to identify f of x and g of x. Let's look for our inner function. Our inner function seems to be what's inside, the 4x plus x to the negative 5th. And what's the outer function? Well, we're taking all that to the 1/3 power. So we should get f of x is x to the 1/3, and g of x is the inside, 4 of x plus x to the negative 5th. Okay, so then we're going to evaluate f of g of x just to make sure that our parts are correct. So we're going to plug in g of x, we're going to plug in this 4x plus x to the negative 5th, and then we're going to plug that into f of x, which we should get 4x plus x to the negative 5th to the 1/3 power. And that matches our original equation, so we're good to go. Now we're going to apply the chain rule. So first we're going to evaluate the derivative of f of x in terms of g of x. So we bring our exponent out to the front as our coefficient and subtract that 1/3 by 1, which should give us negative 2/3 here. Okay. And then we're going to evaluate g prime of x. So we're going to take the derivative of 4x plus x to the negative fifth, which, again, we're just using our power rule, should give us 4 minus negative 5x to the negative 6 power. So then we get our last step. We're going to find the product of those two parts. Our 1/3 times 4x plus x to the negative fifth, all to the negative 2/3 power, times 4 minus 5 times x to the negative 6 power. We'll multiply those two together. So again, we get our 4 minus 5 x to the negative 6 is staying in our numerator. However, this x to the negative 6 tells me it needs to be in the denominator, so that's how it ended up there. This 3 in our 1/3 comes down to our denominator. And right here, our 4x plus x to the negative fifth to the negative 2/3. Well, this negative 2/3 tells me I'm going to have to throw this into our denominator. So this entire polynomial ends up down there. And then this x to the negative fifth tells me that individually needs to go into a denominator or flipped into the reciprocal. So that's why that x to the fifth is down there. So we should get that dy dx equals 4 minus 5 over x to the 6 all over 3 times quantity 4x plus 1 over x to the fifth to the 2/3 power. Okay. Now it's your turn. So go ahead and try differentiating these problems based on what I've taught you so far in this lesson. And then bring what your solutions to class. If you have any questions, concerns, we'll go over those. And then be prepared to work more in class on some more rigorous problems.